Hi class, in this video we will introduce the idea of light as a particle. So you've just read about three phenomena that are inconsistent with the wave nature of light. They are blackbody radiation, which is the observation that black bodies, such as a stovetop, lava, even the sun, all emit electromagnetic radiation, and that radiation is dependent on the temperature. The other observation is the photoelectric effect, and this is observed when light is shined on a metal surface and electrons are ejected. And those electrons are ejected if that light is of a minimum frequency. And the third observation is that of line spectra, which is when certain wavelengths of light are emitted from excited atoms. The first scientist to contradict the wave nature of light was Max Planck. He was a German physicist, and in the late 1800s, he was experimenting with blackbody radiation. He proposed that light comes in small packets known as photons, and these photons have certain energies, and that the energy of an individual photon is proportional to its frequency. Now, classical physics would say that the energy of light was proportional to its intensity. And remember, intensity would be related to brightness. But that was not the case as he observed with blackbody radiation. So he even went on and in 1900 published a paper that said that the energy of a photon was equal to h nu, where h is what we know as Planck's constant, a number that's calculated to be 6.626 times 10 to the minus 34th joules seconds. And if we want to know the total energy of photons in a system, the energy of n photons is going to be equal to the number of photons times h nu. And n here is going to be an integer value. We can't have less than one photon, so it would be an integer value greater than 1. A few years later, Einstein was doing work on the photoelectric effect, and in 1905, he found experimental data that supported Planck's proposal. So at this point, we now think of light as both a wave and a particle, and this is known as the wave-particle duality and is foundational to the field of quantum mechanics. So why do we care about the energy of light? Well, the way that light interacts with matter depends on its energy. So for example, gamma rays, having very high frequency and therefore high energy, will interact with matter differently than, say, radio waves, which are of low frequency and of lower energy. So the gamma rays are fairly harmful if we were exposed to them. Gamma rays come from the sun and other stars, as well as from atoms that are radioactive. And excessive exposure to gamma rays can be damaging because they're able to damage biological molecules. Radio waves, on the other hand, are used all over the place. They're used in our cell phones, they're used to communicate via radio signals and television signals. So these are all around us, and they're generally not harmful because the energy is so low. I'm going to ask that you be able to do calculations to determine different variables associated with different types of light. So we should be able to calculate energy, wavelength, frequency, or even the number of photons. Let's take a look at an example. The first problem I have for you is related to UV light. Let's say we have ultraviolet light with a frequency of 6.8 times 10 to the 15th hertz. Keep in mind that 1 hertz is equal to 1 reciprocal second. That'll be something we need to keep in mind when we're looking at canceling our units within the calculation. I want to know what the energy is of this particular frequency of light. So we know Planck's relationship that the energy of n photons is equal to nh nu. Okay? So if we want to know the energy of a single photon, we can take this equation and plug in and solve. So the energy of an individual photon will equal h nu because n will be equal to 1. So I plug in my value per Planck's constant, 6.626 times 10 to the negative 34th joule seconds. And that number is given on your constants and equation sheet that will be available to you during exams, so it's not something you need to memorize. We would add in our frequency here as 6.8 times 10 to the 15th reciprocal seconds, and therefore my second units will cancel. We'll be left with units of joules, which is a unit of energy, so that's great. I can kind of approximate my answer now. If I take minus 34 plus 15, we're talking about minus 19. So I should have an answer from my calculator that's on the order of 10 to the minus 19th power. If we go ahead and calculate this, we get 4.5, accounting for rounding and significant figures, times 10 to the negative 18th joules. And this is close to our predicted value, and the reason that it is different is because if we take 6.626 times 6.8, we get 45, and we've moved the decimal, which changes the exponent here. So 4.5 times 10 to the minus 18th joules would be the energy associated with UV photon having this particular frequency. The second example I have for you is related to a sodium lamp. Sodium lamps are often used as streetlights. So if you ever see that kind of orange glow coming from a streetlight, it's due to the presence of sodium in that light bulb. And sodium lamps emit wavelengths of 589 nanometers. So my question for you is, what is the energy of a photon having a wavelength of 589 nanometers? We know we're asked to calculate energy, and we're given a wavelength. So if we look at my energy equation, I don't see wavelength present at all. But we do have this other equation that we introduced before, that the speed of light is equal to the wavelength times the frequency. So if we rearrange this equation to solve for frequency, frequency is equal to c over lambda, then we can combine these two equations to give one equation that relates energy and wavelength. And this relationship, that energy is inversely proportional to wavelength, is a key concept to keep in mind. So when we're thinking about even just the visible spectrum, ranging from 400 to 750 nanometers, that blue wavelength of 400 nanometers is going to be of higher energy than the red light at the opposite end of the visible spectrum. So we have an equation now that relates wavelength and energy using two constants. So we plug in our values, 6.626 times 10 to the minus 34th joule times second, times the speed of light, which will be given on your equation sheet again as 3.0 times 10 to the 8th meters per second. So we see our seconds unit canceling. And then we're going to divide by my wavelength, 589 nanometers. So we would cancel my length unit. But there is a problem, right? Nanometers doesn't cancel with meters. So we're going to need to do a conversion. So there are 10 to the minus 9th meters in 1 nanometer. So this would be 589 times 10 to the negative 9th meters. And I can go ahead and plug that in here. This isn't correctly reported in scientific notation, which is completely fine because I'm just going to use this number in a calculation. So we could write it as 5.89 times 10 to the negative 7th. It doesn't really matter for the purposes here. If I calculate this out, we could approximate my magnitude again. So minus 34 plus 8 minus a negative 9 should give me about 10 to the minus 19th. And if we calculate this out, we get 3.37, which would round to 3.4, and accounting for sig figs, times 10 to the minus 19th joules. So you'll start to see a trend, some common numbers popping up, and that is this order of magnitude, 10 to the minus 19th joules for a single photon. And this is going to be pretty consistent for photons within that visible spectrum, and to some extent the UV and IR regions that closely border that section. But If you're calculating the energy of a photon, you want it to be on this order of magnitude. That's a good sign that you've done the calculation correctly. There are several other practice problems that I'd like you to try. So if you have any questions as you complete them, please reach out and send me an email, post it on Piazza. Otherwise, thanks for watching.